Data that passes a normality test is not always good enough to use. That's just a simple fact. Trends and frequency will throw you off, and you will get a type 1 or 2 error if you do not address them. Trends and frequency can make normal data fail the normality test, as well as make non-normal data pass a normality test. It also inflates your standard deviation and moves your mean. This video will show you how to find trends and frequencies and deal with them so your data is usable. It also teaches you how to minimize your standard deviation so that you can detect changes in your data more quickly. So before doing a normality test, check to see if your trend is constant or changing and if your frequency is mono or multi. So there's two variables here in addition to normality. Trend is constant, that means it's pretty flat. Changing means you have an upward or downward trend. A frequency can be mono, meaning there's no seasonality. The data is one set of data. Your frequency could be multi, which means there's seasonality. It could be by shift, by day of the week, by line, months. There could be special causes going on. And we'll talk about that in a little bit. So if your data is not constant trend and monofrequency, then your standard deviation will be inflated, your mean will be off, and pretty much guarantee you'll not see a change when there is one, or you will think there is a change when there is none. So a changing trend may make data pass a normality test, um, uh, but it's not usable. And unknown multi-frequency may also make your unusable, make your data unusable and may pass a normality test. It could also fail a normality test when it is a normal. That's why I look at all data with three different chart types prior to using it, and I slice and dice it. Take a look at the next slides. So a line chart with the oldest data on the left and the newest on the right will show you if there is a changing trend. If there's a trend, you must calculate the trending mean and the trending control limits. I'll show you how to do that later in the video. So an XY chart with different colors for different sources of frequency will show you if the data is usable, or if you have actually two different sets of data, and that's what I call multi-frequency. Lastly, you check out your histogram just to get a feel for how it looks. So here's an example of a constant trend set of data with monofrequency. Notice how the line graph in the upper left looks flat, which means it is constant. It's also fairly random in its movements, so it may not have a frequency. The XY scatter has first shift and second shift in different colors, and the populations are overlapping. Now, shift isn't the only one. You should look at every possible scenario that you can to see if you've got some kind of frequency. The histogram, like I said, looks pretty normal. The JB or Jacques-Barré test for normality p-value is 0.38, which is greater than 0.05, so the data is normal. So far, so good. But this does not mean that the data can be used. We must look for any data that has attributable cause that may inflate your standard deviation and move your mean. We'll show you that a little bit later. So this is an example of a constant trend set of data with multi-frequency. Notice how the line graph in the upper left looks flat, which means it's constant, but it does have a weird look to it, kind of like a sawtooth pattern. This usually indicates some sort of frequency somewhere, so you should start slicing and dicing the data. You can do that by putting it in an XY scatter graph. In the upper right, we can see that there's a multi-frequency by shift. The orange and the blue are two different shifts, and there's just a little bit of overlap, but they're two separate sets of data. And there could be any type or number of frequencies, so just slice and dice your data looking for it. The histogram does look weird, and it's what we call bimodal because it has two peaks. This, again, is usually an indication of some sort of multi-frequency. If you look at our Jacques-Barré test for all of the data, it's 0.03, which is below 0.05, which means it's not usable and it's non-normal. But if you separate the two shifts and put them on separate graphs and do a normality test, you'll find that both sets of data individually will pass a normality test, and you can use them. So you've got two different sets of data based on your um, shift. So when you separate the shifts, you have constant trends, monofrequency, and normal data. Again, that doesn't mean you've got the best standard deviation. I'll show you how to calculate that, how to clean that up in a little bit. So this is an example of changing trend set of data with monofrequency. Notice how the line graph in the upper left is trending down. This means the data is a changing trend. The XY scatter also trends down and has first shift and second shift in different colors, and they are mixed up and overlapping on each other, which means that as far as shift is concerned, it's a monofrequency. But slice and dice, look for anything that might exist. The histogram is looking a little odd due to the changing trend. What's weird here is that the JB or Jark-Barrett test for normality is 0.08, which is just above 0.05. So the data technically is normal, but it's pretty close to not being. It is not usable because of that changing trend. That changing trend is making the data set appear more normal than it is. Um, we will need to account for the trend in order to have good data that we can use. If we fail to account for the trend, then we're going to have a hard time detecting any change due to the standard deviation being inflated and the mean being in the wrong place and being static as opposed to trending. Once you account for the trend, you'll have good data to use for calculating the trending mean standard deviation for a control chart. You can also test for normality. So once accounted for, you'll have a trending mean, trending control limits, and then the frequency is already at mono, so we'd be okay. Um, Once we get the trending mean and trending standard deviation limits, we'll be in good shape, but we will have to make sure that's clean. The test that I'm going to show, the method I'm going to show you how to make sure it's clean works the same here. It's just a little bit more difficult to see, but it works the same way. So here's an example of a changing trend set of data with multi-frequency. Notice how the line graph in the upper left is trending down and has that sawtooth pattern that we saw earlier. The XY scatter has determined that shift is what's causing our multi-frequency, and each shift should be a unique set of data. So the histogram is not too odd looking due to the changing trend and the added range from the multi-frequency. See, it doesn't look too bad. Surprisingly, the JB or Jark-Barrett test for normality, p-value is 0.36, which is greater than 0.05, so the data is normal. But this data is not usable due to the trend being changing and the frequency being multi. Having both a changing trend and multi-frequency will skew a data and a histogram, making it appear normal when it is not. Before we can use this data, we must separate the two shifts and look at them individually. Once we have data representing a monofrequency, we will have to calculate the trending mean and standard deviation to get the trending upper control limit and trending lower control limit. Once we get the trending mean and standard deviation and the limits, it will pass a normality test. Each shift will pass a normality test. So that would be great, but we still might have an inflated standard deviation. So that's what we're going to show you next, how to clean that up. So what we're looking for is special cause data that can be removed from a data set. We use special cause detection to calculate the mean and standard deviation. And like I said, this works for a changing trend as well as a constant trend, but I'm going to show you constant trend because it's a little easier when you're first starting out. But once you do this a few times, this next step, it will be easier every time. So you can only remove data for a verified special cause. These special cause variations we look for are one data more than 3 standard deviations from the mean, 2 of 3 data in a row more than 2 standard deviations from the mean on the same side, 4 of 5 data in a row more than 1 standard deviation from the mean on the same side, and lastly, 8 or more data on the same side of the mean. Notice in cell B1, the JB normality test is non-normal at 0. When you open up that file, then it'll probably be a lot easier to see it. So cell B1, 0, right? If you look at the standard deviation in cell J1, it's 26. Okay, and if you look at the mean, it's 382. The green cells in row 1 are the original limits. I just copied and pasted them in here so that you can see as the light green cells change as I remove data that is statistically significant at a 95% confidence level. So what we're going to do here is we're going to look at anything weird on this graph. And we can see that there's some data below the control limit, data point 21. So let's look at data point 21, and actually 22, 21 and 22 are 2 of 3 below 2 standard deviations, which means they can be removed since they are statistically significant at 95% confidence level for special cause. And then let's go back over here. 35. Where's 35? Cell 35 is below 2 standard deviations, which is 337. 35, 36, 37, they're all below. So we can remove those. Because those are all statistically significant at 95% confidence level. That means that there's special cause variation. We don't know what happened. We could ask manufacturing what happened, or whoever that gave us the data. They might remember, but it's probably so long ago they probably don't are not going to remember. Now let's look over here. We've got a group of data here that's kind of below the mean, and then we've got a group of data here that's below the mean. And let's go down here and look at about, where's the first one that starts out here? 67. 67 to 75. So they look like they're all below the mean. And here's our new mean. They're all under 386. So we're going to remove those. That's special cause. That's 8 data points or more on the same side of the mean. Now let's look. There's another group over here that was hanging out. Data point 50 is more than standard deviation. 51. Let's look at data point 50 then up. Data point 50 is 350. We've got 50, 51, 2, 3, 4. Looks like we've got all of these are less than 1 standard deviation. So we can remove those because that's statistically significant. Now look how our standard deviation is changing and our test for normality. And look at how our our mean has changed and our range has changed. Now we've got one more here, kind of hanging out there, 334. That's 0.23. That's below 3 standard deviations. So there we go. And it looks like the rest of the data is pretty normal. We got some, I don't see anything else that's special cause. So what we did was remove some data that was more than 3 standard deviations. A couple of sets of data that had 2 out of 3, more than 2 standard deviations away from the mean. A couple of sets of data, or a set of data that had 4 out of 5, or actually it's 5 out of 5, that were more than 1 standard deviation. And then we had 9 sets of data that was below the mean. So we removed all of those because they're all statistically significant at 95% confidence level. Notice the normality test now is a 0.49. And then standard deviation is now 18, which means we've got a much better chance at detecting something statistically significant. Our mean is now 391. See how it shifted? It moved up. So don't worry. This is not the easiest thing to do, but it will get easier the more you look at it. Just take your time and look for one um, statistically significant type of event at a time. Always start with the data that's furthest away from the mean and work your way towards it. Eventually, everything will be inside there. So I am going to go to the next slide, or actually, we're going to go to the changing trend tab. Now, column B is our metric, it's our data, okay? And it has a trend because you can see it over here. So here's column B, and our test normality test is 0.89. So that's not bad, but this changing trend over here is going to give you an average of like 1500 and in control limits that are flat. And as you can see, as you progress over time, it's just going to go below that lower control limit no matter what. And then if you were to change it and go up, it's going to be a long time before you notice anything. So you have to account for that trend, and I'm going to show you how to do that now. So one nice thing about Excel is you can select some data, and you can add a trend line. And I like to do this. And you can select something that gives you the highest R squared value. So that trend line looks pretty good. Um, Once you've got that formula, you can use it to start calculating your trend. So under column F, use that formula. I'm going to come in here and you can see I use the formula to actually calculate my trend. The only thing is when you're using an Excel formula, it always has one on the furthest to the left and then it increments up. So the x-axis has to be 1 through whatever and whole numbers in order for this to work. But once you do you put the formula inside here, you can create a what would be what I would call your trending mean. And once you've got that, then what you do is you take the difference in your metric, you take that away from your trending mean. So your trending mean minus your metric gives you this factor. It's the same for every one of these, just keep doing it for all of them. Then what you do is you use this row or this column G to calculate your standard deviation. And if you look over here, the standard deviation in the original data was 318, but it's actually 315 once you account for the trend. Then you can use that to take the standard deviation of this column and you just multiply by 3, and then you add that to the trending mean, and that gives you your upper control. You do the same thing for your lower control. It's basically the standard deviation of this column, and you add that times 3. You multiply by 3 and add it or subtract it from your trending mean. That gives you your lower control limit, and that's what these are here. And then now you can see that if you start making changes, you can see them or detect them much more quickly. So now that you've accounted for the trend and used it to calculate a trending mean and a trending standard deviation limits like upper control, lower control, +1, +2, -1, -2, you can go back to what we did in the previous slide and start looking for those special cause variation. Just look for the stuff that's maybe 8 in a row below the mean, even if it's trending down. Look for 4 out of 5 less than 1 standard deviation or greater than 1 standard deviation away from the mean. 2 out of 3 greater than 2 standard deviations from the mean, and 1 greater than 1 standard or 3 standard deviations from the mean. So if you take the average of all the original metric data and the factor data, you get a result in column J. This is where you're going to start doing your normality test. So what you do is you take the average of all the uh, the original metrics, and then you add the factor for this number. You do the same thing here. You take the average of all of those, add it to that factor, and you create all these numbers. Then you do a normality test on these numbers, and it's 0.93. So that's pretty good. So if you want anything as far as files go, just email me. I'm always happy to share. The next video shows the use of an eye chart to track and ensure changes are what we want and that they stay in place. If you found this video useful, like it, subscribe to the channel, and share it with anyone else who may find it useful. If you didn't find the video useful, subscribe in the hope that an upcoming video will be. Eventually, we're going to go through Lean Sigma, Six Sigma um, projects as well as the tools needed to support them. Remember, a wise person learns from their mistakes, while a genius learns from the mistakes of others. I'll see you soon, and until then, keep your data clean.